So it's homework that's due on Wednesday. And the homework is to basically visualize your basic blocks. So building a visualization of this and then being able to take a look at it. So we're building a graph and we're going to use GraphViz to do that. The basic idea is the basic blocks are chained together. Either they flow directly into another basic block, either because they just flow straight into another basic block, or because they get there via a jump or a branching instruction. So go find the basic blocks again and then chain them together. And if you don't know where a basic block goes because it has a return or something like that at the end of it, then that's fine. You just don't know in that case. Build a digraph. We're going to use GraphViz to visualize it. Not all GraphViz visualization algorithms are created equally. So in particular, if you try to generate a graph for something rather large, like let's say Bash, you will end up with a very large graph, and visualizing that using something like Dot is not going to work great. But that's okay because there are tools in GraphViz for visualizing fairly large and nasty graphs. And one of them is SFDP, which is a spring embedder algorithm. And you can use SFDP to try to visualize it, and it will generate a result before the heat death of the universe. Smaller things, it should go just fine. You shouldn't really have much trouble with that. The example I gave you the other day was, I sent out by email, I guess last night, was this little example. graphtest.asm. And there shouldn't be anything too outrageous present in the code here. It's just a little example for you to compile and try your stuff out with. It's got an unreachable basic block right here. There's no way to get to start. Nothing reaches it. It's got some trash data bytes here. 48 in particular is a good byte because it is the prefix byte, a common prefix that switches you from, let's say, using EBP to using RBP. It's a fancy version of the mod RM. Here's main. This is where we actually do start. And it just does some more or less random stuff. It pushes RBP, it moves RSP into RBP, and then it zeroes out EAX. It does a shift left of RAX and 1. Okay, so that's going to shift it left. So picture a string of bits in your head. Those bits are all zeros because it used to XOR it with itself. We shift it left by 1, and then we do a jump above or equal. So what's going to happen is we're going to shift a 0 into the carry flag. You should be able to know that part from the shift left, that a 0 is going to end up in the carry. And then what does jump above or equal do? It turns out what it does is check the carry flag. That's all it does. You can go back. There's a slide in one of the previous classes where I went through how all of these conditional branches work. It's somewhat important stuff because it can be exploited. So this one just checks the carry. And if the carry is clear, it takes the jump. So what's happening right here is this little XOR and the shift left and this jump above equal. That's an opaque predicate. You wouldn't usually see them all right here close together like this. You'd space them out with some other stuff in between them. But this is an opaque predicate that will always take the jump to dot skip. So then the jump 0 to tail, what is that? That's nothing. It never happens, so we don't care about it that much. But your code will, because your code does not figure out that this is an opaque predicate. We'll see how to do that. We're running out of class, but if there's time, we'll see how to do that. So after that jump 0, we have another little random data byte just to mess up this assembly. And then we have skip. And skip just loads the location of message into RAX and then puts that in RDI. This calls a print function, so we have a call in here that your code should see. We put 64 in ECX, we put a big number in RSI, and then we start printing it out in binary, so we put a buffer together. Here's another basic block. We call a routine called .BitShift. We increment RDI, we loop the top. Another basic block here. We put 0 at the location pointed to by RDI, which actually just null terminates the string we just created. Print is in another section, so we call it. Here's tail. There's a branch to tail up above, that J0 to tail. That's not taken because it's OPEC predicate. Well, here it is down here. So the idea is that your code should be able to split right here and find another basic block right here. Here's bit shift. You should find bit shift because of the stuff up here. It just does some bit shifting. Oh, I guess I should talk about what it does. So we shift left RSI 1. So this takes the high bit of RSI and puts it in the carry flag. This puts hex 18 in AL, and then this RCL is a rotate, which takes the carry flag and shoves it in the left side of AL, moving all these bits over. And when it does, you end up with an ASCII 0 or ASCII 1 character in the buffer. It's a weird trick. And then we put that in the buffer and return. That's all that little routine does. We have another section called subroutines. It's not the text section, so your code should not be exploring it. It didn't have to be exploring it. And something you might try is, you see we've got a fairly long section declaration here, right? Section, subroutines, is not a dot because it's not a system one. Exec, no write, align equals 16. And you might be able to guess what happens if I drop exec. If you can't guess what happens if I drop exec, you should try it. It just prints out something. Then I have a data section and a VSS section, and that's it. And that's the entirety of this. It should be buildable if you type the name correctly. There we go. And it should run. Strangely enough, it should do exactly what it's supposed to do, which is print out the contents that we set in the register in binary. And you should be able to do blocks on it. There we go. And there are the blocks that make it up. There shouldn't be all that many. You can see how they're broken up. Here's that jump above or equal to 1159, which is right there because it's now a leader. But the system doesn't, your little code doesn't know this is an opaque predicate, so it assumes I might flow forward and get this, which is a jump to 11.9e. And if you look, you'll find 11.9e in here as well. And if you didn't take that, you would then go ahead and do 11a2, and 11a2 is the return. So this is these are the garbage bytes after it. Then we have this load effective address and some other stuff here, 1159. We also have 11.5a. So you may notice that only one of these is the right one. 11.59, this is the basic block that actually gets executed. 11.5a is not the basic block that gets executed. This is just something that your code will see because it thinks you could fall through these and not trigger them. So 11.59 is here, load effective address, notice the RAX down here, load effective address, notice the EAX. They're off by 1 from each other. That 1 is a prefix byte I put in there just to indicate the prefix bytes. Otherwise, they sort of sync up and flow forward. This is a good thing to do if you're trying to trick people because it looks like there's plausible code in both directions. Nothing is too weird. So then you've got the little call block. Let's move. Down here is the little subroutine we have that gets found because you evaluate the call. And the print subroutine is nowhere in here because it's not in the text section. It's just not in there. Same thing for graph. If we do graph test, we should get a little tiny graph out that looks something like this. And if you save that to a file, and can type, which I can't this morning, let's make it a PNG. There we go. Then we should be able to open that up. If I can remember where things are, files. Oh, I'm in homework. I'm lost. I have not had enough coffee this morning. There we go, graph test.png. So let's go ahead and open that up. Oh no, I don't want to open up GIMP. I guess I will open up GIMP. Anyway, there it is. So these you see are all connected. So the system thinks this block can flow into this one or this one. This is, you see a little path that leads to 11.5a. 1180 has the loop in it, so we get a nice little loop on that one. Let me flow out when we're done. This is the subroutine up here. Right? No basic block directly flows into it. It's called, and so it just winds up by itself over here to the side. Hope that makes sense. All right. So that's that. Let me think about some hints for you. If you haven't already done it, you should definitely be working on it. It's trivial-ish, maybe, depending. There's a lot of different ways that you can keep track of this information. You could try to keep track of it during pass one. That way is a little tricky. I wouldn't recommend it. What I recommend you do instead is you do it subsequent to pass one, like when you're processing all of them later on. You'll be processing them in order by their address. And so at the, you can just look at the end of each basic block to figure out what happens. It'll be a jump, or it'll be a return, or it'll be a halt, or it'll be a, if it's not a conditional branch or a loop, if it's none of those, then it just flows straight into the next block, and that's the answer. So you wind up with one or two arrows in here, depending upon how the block ends. And you can see that from the example I sent out. The example is also posted on the homework site, along with the solution to the previous homework. Whew. Questions about the homework?
Do you have a link to the, I found some documentation by searching, but do you have like a direct link to like a PDF or something we can refer to when trying to use GraphViz for the first time?
So I don't. The GraphViz site has, the main thing on the GraphViz site is lots of just helpful examples. But really, all the syntax you need for GraphViz is actually right here. So you just say digraph, give the name of the, in this case, I just give the argument. So if I pointed it to user bin echo, this would be user bin echo in here. Inside the curly brackets, you list the nodes and the arcs. This is how you specify a node. You just give it the name and quotation marks. And this is how you specify an edge. You just give a node name and another node name. Doesn't have to be declared. This is sufficient to declare it. And a little ASCII arrow between the two, right? Minus, greater than. And that's it. And one per line, and you're done. And that's all the syntax you need. Oh, go ahead.
My question is, that doesn't, I'm not certain if that would work like dynamically. That looks like a very static statement right there.
Yep.
Say again?
This just creates source code for it. This is basically source code processed by Dot or any of the other processors in the GraphViz library to create a static graph.
Oh, okay, right.
Okay, so that's it. Nothing too super elaborate. Other questions about the homework? Cool. When you have questions about the homework, email me. Don't wait until 1 a.m. or 2 a.m. to do it. There's a slim chance I won't be awake then. So I recommend you do it before then. Okay, back to Mycroft. When last we left, we were talking about this paper, type-based decompilation. When you're doing program analysis, this is a class about program analysis, basically. And it's about analyzing, in this case, compiled programs. Compiled programs lack certain information. Part of the information they lack is types. You're just struggling in the dark most of the time with, what is in RCX now? Is it a counter? Is it a pointer? Is it an integer? Is it something else? What is it? And figuring that out can be pretty tough. This is the way to do it. So after Mycroft gives you the intuitive example we went through last time and explains some of the methodology and how this works, he gives you a longer example. And the longer example is not a very long example at all. It looks like this. So up here, for some reason, he has semicolons as his comment character in his register transfer language. This is a big comment. And the comment is, oh, here's my C source code that I use to produce this function down here. And so he basically says, here's a small C program. I'm going to compile it to my RTL, which will lose type information, and then we'll see what we can recover. See if we can recover this program, maybe. That'd be great. So it's int F, and sure enough, this is called F. And then this shouldn't look too strange to you. This should look a little bit like the assembly we've been looking at, but you have to keep in mind it's not assembly, it's register transfer language, and it's not Intel assembly, it's Mycroft's invented language. Just the way the world is. So up at the top, we have the C source code, and it might be worth thinking about how you would go from this to this, because it's not necessarily super clear in the paper how you get from something up here to this. Let's do that real quickly. So here's the C source code. Shouldn't be terribly complicated looking to you. I have a struct called A, which is a terrible name for a struct, but that's what he's calling it. It has a head and a tail. A head and a tail. The tail is a pointer to another struct A. This looks so much like a linked list that if it doesn't immediately look like a linked list to you, you should probably, I don't know, go back and take another data structures class. This is clearly a linked list. And so here we come into F. F takes one of these linked lists, right? It takes a pointer called X to a struct A. So an instance of this. And it sets R equal to 0. And then it goes into a for loop. And there's no initialization, which is fine. It checks to see if X is not 0. What is X? Oh, X is this pointer. So while this pointer is not null, it's going to go ahead and add the head value to R. And the head is an int, so that makes sense, right? R is an int, head's an int. It adds whatever's in the head to R. And then it's going to set X equal to the tail of X, and then go back around the loop again, check to see if this is null, do this, go back around the loop again. And so you get this nice little backward pattern through the for loop. You terminate when you hit null. So what is X going to be? X is going to be the tail of something. Right, there it is, the tail of something. You're going to hit null, and that's going to stop. And otherwise, it's going to sum up the things that are in the head of your linked list and then return that result. There you go. So your linked list holds a bunch of integers. This just sums the integers in your linked list, terminating when it hits a null. Pretty easy stuff. Let's compile it. And so a few little pieces of trivia here that are maybe worth mentioning. I'm sure you're all C experts. You should be. That's great. So up here he has int R equals 0, just floating out here by itself. Could we take this and put it in here in the initializer? Just take this whole line and just shove it in here. That will not work, and you should know why it won't work. Can we move this inside the for loop? Well, we can in fact do that. where would it go? Well, this code has to happen before this code happens. So we would take this line right here, put it right before this line, and put a comma between them. I'm sure you're all familiar with the comma operator in C. Okay, a few bits of C trivia for you. So let's grab this loop and let's first work on compiling the loop. And a compiler is going to take this and it's probably going to do the following things. It's going to take this loop out and it's going to convert it to a while loop. And so what does this look like? This looks like while x is not null, do this and then do this. And so that's in fact we write down here. There we go. So you do the body of the loop and then you do the loop increment at the end of the body. And then this is the condition for the while loop. There's nothing to put up here, so there's nothing to worry about for that. While loops, you seldom see while loops directly in assembly. Usually what you see is like do until or do while loops. So let's unroll it once. And so unrolling it once looks like this. We check to see if x is not null. If it's not null, then we have a do while. And the do while is just the body of the original while loop right here and the same predicate as the while loop. There you go. We just unrolled it once. So that the branch condition is here at the bottom of the loop. And so we branch back to the top. Do the body, branch back to the top. That's the assembly friendly way to do it. Once we have that in place, we can pretty much do the rest of it directly. Mycroft tells us that the arguments come in the registers in order. So X will be in R0. We know that. And there's no other arguments. So R0 is the only thing used for an argument. So we need a register to hold this thing. Let's make that R1. And so sure enough, we put 0 in R1. Remember in the Mycroft language, it is source destination. It's backwards in Intel, but it's this way in Mycroft. And keep in mind our assignments over here. So once we've done that, now we immediately have a comparison. And the comparison looks kind of weird if you look over here as to what's going on. But if you look down here at the unrolled loop, you can see what's happening is this is the test for the enclosing if statement. So we check to see if R0 is null. If it is null, we branch down to L4F2, which is not an uncommon made-up name for a target in compiled code. L4F2 right here. We move R0 into R1. What is that about? Come back to that. And we return. Oh, sorry, we move R1 into R0. I'm thinking Intel. Sorry. So R1 is the R. We put that in R0 because that's where the return value goes. And then we return. That's it. Nothing more to it. So then we come into the body of the loop. Right? If we didn't take this branch, now we're in the loop. This is the loop. And the first thing we do is the body of the loop, which is taking X, getting the head of X, and adding that into R. So what is R? R is R1. So we should see that we add stuff into R1. And in fact, we do. We take R2, add it to R1, and store it in R1. What's R2? R2 is we load a word from R0, offset by 0, into R2. All right, so the head is the first thing in the structure. It's the first word in the structure. So it occurred offset 0 into the structure, and R0 is that pointer to the structure, right? R0 is holding X. I'll put that on R2. Once we've done that, we have to go back and advance X to the next pointer. And since words in Mycroft language are 4 bytes long, 32 bits, we take R0, we offset by 4, and we put that in R0. So this is my X gets the tail of X. Once again, I'm now down at the do while predicate to check to see if X is null. So I do the same thing I did up above. I check to see if it's 0. And if it's not 0, I branch back to the top. Otherwise, I fall through. I move my return value into R0 and I return. That's it. So that's where the code comes from. That's why if you look at this and you look at this, you might wonder why this thing shows up twice. It shows up twice because a common compilation technique is to unroll a loop once to get this kind of structure. Whew. So one of the first things that Mycroft does once you have this code over here, his analysis depends upon this being in static single assignment form. And if you remember static single assignment form, you remember that when we have branching, and we definitely have branching here, there's a branch if equal and there's a branch if not equal, we need to introduce phi functions to account for that. So here's the flow graph for Mycroft's code. There's initialization. Here is the if then else. Here's the do while. Nice little structured program, write a sequence, an if then else, a do while. That's it. Easy stuff. And I've accumulated the basic blocks into the little cells here. Here are the join points, right? These are the branch targets. And so you can sort of call them out immediately as obvious places where there are joins. And we need to invent phi functions for them. And we can invent phi functions for everything, right? We use R0, R1, and R2 in the course of this program. So we can have all three here if you wanted, that would be fine. It turns out that we can show that some of them aren't live, like R2 is not live. Like the first thing you do is write to it, right? This is the destination on this side now. The first thing you do in the body of the loop is write to it. So it's not live. We come into the loop, so we don't need a phi function for it. And what about down here? We don't have a phi function for R1 or R0. Well, R0 is not live because the first thing we do here is override it. And if you remember how liveness works, we've just destroyed the value that was in here. So the value coming in R0 has no effect on the program. So we don't need a phi function for it. So we need two phi functions here and one here. If you didn't figure that out, if you were writing an algorithm to do that and you didn't want to take the time to figure live variable stuff out, there is another way to do it, but it's more complicated than I want to explain. I think it's actually described on the Wikipedia article on live variable analysis. It's frontier propagation. You don't care. You would just do them for all, which is fine. It won't hurt anything if you have them for all. It just means that there's more stuff to fool with. All right. So we can put the phi functions in here and we'll just shove them in just like we have it right here. There we go. And remember how these work. In this case, I've used a move because I felt like using move with it. And so I'm going to pick one of these two. Right? The phi function just says, pick the right one and put it in here. Okay. So let's get on with building the SSA form. Mycroft likes to put letters on the end of things. Fine, that's what we'll do. So R0 becomes R0A, R1 becomes R1A, and so on down the line. And we work our way through it. You've all seen this before, so I'm just going to page through here. And there we go. And now we have it in SSA form. And once we have it in SSA form, we can begin to use Mycroft's little table here. Okay, here's his table for the little snippet of instructions that make up his RTL. Nice, simple, small RTL. A question you might ask yourself is, given this, and let's say you have one additional branch condition, branch if not equal, let's say. Is it Turing complete? You should be able to figure that out. And the answer ought to be, it's as Turing complete as this program can be. Right, because we've got 32-bit words in here. We can move around. We can evaluate stuff. We can do math on them. So it's not just is it Turing complete, it's also got some undecidability baked into it because it looks like we could maybe encode piano arithmetic with it. It's Turing complete because we don't set any limits on memory. If I limit memory to some finite amount of memory, then it's technically a finite state machine. But, for all practical purposes, we have a nice Turing complete RTL, which means we have all the problems associated with Turing machines baked into this. All right. But we have constraints for each one of these little things. And the idea is we would go through the code and we would apply the constraints. So up here we have this move, and we look down here and there it is. And so this gives us a constraint. And so we'd write the constraint up here. The type of 0A is equal to the type of R0. There we go. He uses little T's in front of it to indicate its types. For the next one, it's a little different. This is not a register thing. This is putting a constant 0 into a register. But the constant 0 is special. So we look all the way down here, and moving 0 into something has its own specially called out example. And he means, when he says 42, he means really any integer. He just picked 42 because of Hitchhiker's Guide to the Galaxy. So we put 0 in here. That means that the type of R7 could be an int, or it could be a pointer to something we haven't seen, a pointer to some other type, alpha double prime, and that's to distinguish it from alpha prime and alpha up here. So it could be an int, or it could be a pointer to a type. We do a little pattern match on this, and we wind up with this condition right here. T1A could be an int, or right, the big V is disjunction. It's an or. Type of 1A, and I'm not sure why that's a different looking A than that one. I think it's not italicized. Could be a pointer to some alpha we haven't seen, a type variable that maybe we'll resolve later, maybe we won't. Let's see. We proceed the same way. We put 0 in here, same basic condition with just slightly different parts. Different alpha over here, alpha sub 2, because we don't have any reason to conclude they're the same. Down here, I've got these moves. So I have two possible moves. Maybe I'm moving A into B, or maybe I'm moving C into B. And so I'm moving A into B or C into B. It could be either one of those. Same thing here. Down here, though, I have a memory expression. And so when we look down at this table, we find load word. We match it all up. So 0 matches the N. So we should see a 0 in here. And in fact, we do. R0B is the R3. And so we should see T0B here. And in fact, we do. And R2A matches R5. So we should see T2A here. And we do. So yay, did that correctly. So we get that little expression. And we march through the rest of them. And pretty soon we've annotated the rest of the program. And this is a system of type constraints. These things constrain, but don't necessarily determine the type associated with this. In fact, you can tell that because we have some different possibilities. It could be an int, or it could be a pointer. For this add, maybe we're adding an offset to a pointer. Maybe we're adding a pointer to an offset. Maybe we're just adding integers. I don't know, but probably one of those three things. You see they're all connected with disjunction. So there we go. We wind up with a set of type constraints from Mycroft. We still need to annotate the function itself, right? What does F's function signature look like? Well, he uses T99 to indicate the return, and the return is going to be in R0, and we know R0 at this point, the value in there has type T0D, and so there's the type for the return value. And we know at the start, the input's in R0, which has type T0. So there's the type of the only argument we have. And so the type of F is T0 mapped to T99. There we go. And we've finished Mycroft's type annotation. And it should have seemed reasonably not crazy how that's done. So here we have a system of 13 type equations. And there could be one solution to this. That's possible. There could be many solutions to this, right? Maybe I could choose this to be an int or a pointer, and everything else will work just fine. That would be okay. or there could be zero solutions to this. How could there be zero solutions to this system of type equations that I derived from a real program? Think about that one. Think about that. Could there be zero solutions? And how could there be zero solutions? Something fun for you to ponder. All right, so let's start solving this. So solving it will be basically picking types for all of these different little things in here. So the author then walks through how we might do this. And he devotes a lot of time to explaining how you would mechanically solve these in the paper. It's worth reading. You should give it a read. He notes that T0B is T0C. Where do we get that? We got that from right here at line 5. This is one of the things that's possible from our type constraints, right? We know that this is true, and we have that this is true. And when we combine this with line 7, which is this one, and line 9 down here, the two that reference memory, we have that T0C can be T0B, which we know has these pointer structures to them. And so what's going on here? Well, one of the things that's going on here is that T0C, the type associated with this, is a pointer possibly to something of that same type. So here's T0C and here's T0C. Now, we know that the recursion, because you've seen the source code, the recursion here is broken by a null pointer, but your system doesn't know that. If it tries to process that, you might get an infinite regress. So what he does is he talks about a curse check. A curse check is a pretty common little term used for looking at the thing on the left of a production and then making sure that that thing on the left does not occur on the right-hand side of a production. Because if it does, then you have this infinite regress. Pretty simple. And so here we fail it. We fail a curse check because T0C is here, and it's also over here on the right as well. That could be bad. How do we fix this? Well, we notice that these are different parts of memory, different offsets, and we build a structure. So he says, I'm going to build a structure. By the way, if this T0C equals this thing at 0 and it equals this thing at 4, if that bothers you, it's okay. It bothers me too. It's just the way Mycroft decided to do it. Think of it as like partially fulfilled. I tend to think of them as productions. All right, so here we go. We wind up with this struct. We have type 2A at offset 0. There's offset 0, type 2A. And then at offset 4, we have type 0C. There we go. Now, Stacy, you may be saying, if I say this is equal to this structure, it still occurs in the structure. Sure, it does. But I'm going to fix it by just using the name of the struct. Watch this. Watch how clever this is. Type 0C, type 0B. Here's that pointer with the, oh, this fails a curse check. I don't like that. I convert it to a pointer to the structure. Oh, that fails a curse check. I don't like that. I replace it with the pointer name. Suddenly, everything is happy. T0C does not occur anywhere over here on this side because I just bottle it up inside the G. And it turns out that's fine. That's what Mycroft is getting to with his solving the occurs check problem. It seems like it's a funny syntactic fix. It's because it's a funny syntactic fix. It's just the way it is. So the new expression does in fact pass occurs check. T0C can be a pointer to struct G, and we keep going. So from 13, 12, and 11, here's 13, here's 12, here's 11. Why backwards? Because T99 is T0D, T0D is T1D, and T1D is T1A or T1C. We wind up with this. It has to be compatible with both of those. And so going from this world, we have, they must be equal to both of these. Type 99, the return value of the whole thing, has to be compatible with these two types. Easiest way to make these two types compatible is to make them be the same thing. Continuing on in much the same way, we look at T1A and see where it's assigned. We can work backwards because we're in this nice SSA form. T1A is just T1A. We never figure out anything better for it. T1C, however, is T1C. Where is it? Where is it? Where is it? It's in here somewhere. There it is. T1C is buried up in here, and we can find, work it back and wind up with this result. From line 8, we know that since T1B and T1C have to be the same. What does it? Do we really know that? We do. T1B and T1C. Only the second and third clauses can apply, right? Because for this one, T1B is an int, and this one, T1C, is a pointer. So those can't be the same thing. So this one can apply if we're going to honor this. Can this one work? Yep, T1B is a pointer, T1C is a pointer. That works, right? They can be equal. How about this one? T1B and T1C are both ints. That works. They can both be equal. So either one of those will work. Again, we're constraining but not determining. And so there we have it. We can either have this or we can have this. So here's our little rule for T1B. We conclude that T99 has to be either an integer or a pointer. Of course, we've seen the code. We know what the answer is, right? We know it's an integer, but we don't know that from just looking at this. And so it could be a pointer. It turns out that we have to have A5 equal to A1. And you can see that due to line 3. If you look here, you'll see that when we're setting T1A to 1, and then later on, since we know T1A and T1C are the same, we see they have to be the same. The alpha has to be the same. What can we deduce about T0? Well, T0, we have this information right here, and is equal to T0A, and T0A is equal to T0B, and T0B we know is that pointer to a structure we had from the occurs check stuff earlier. So you wind up with this. Type 0 has to be a pointer to a struct G. So the first argument has to be a pointer to a structure G. We don't know what the return value is, though. So we have two possible types for the function. The type of the function could be, if this is what we had, and we know that T0 is this, and we know T99 is one of these two cases right here. If I choose this case, then I don't shed much light on anything. I take a pointer to a structure G, and I return a pointer to some other thing that I haven't specified. That's terrible. I don't want that. Or I return an integer. And so Mycroft calls this a parasitic solution. It's just stuck around. It's attached itself to our math, and it's drug itself through the math along with everything else, but it's not adding any value. It's just complicating our expressions. So in that case, it's like a parasite. So he just throws it away. The arbitrator decides, I'm going to get rid of it because I don't like it. Right? I'm looking for a plausible type assignment. And based on everything I know right now, it could be either one. And of the two, this one is more useful. So he throws the useless one away, and you wind up with this as the result. And there we go. So now it turns out, that is the correct typing for this function, which we know because we saw the source code previously. All right. So all that's all well and good for the Mycroft RTL and for doing it that way. But what about if we're looking at programs written for the x86 64-bit processor? So the x86 version of Mycroft. So before we get too deep into this, it's again kind of it's always worth looking at other ways of doing program analysis, and it's also always worth looking at the output of things like compilers, because you can learn some stuff about what programs look like by looking at what the compiler will do. Different compilers produce different output. Some optimize away stuff. stack frame maintenance, some local variables, all sorts of stuff that may or may not be needed. And some eliminate intermediate results. We've seen that previously as well. Think of all the times in your C code that you don't check the return value of a function, right? So if it's your function in your code and you're never checking the return value, the compiler may actually be able to figure that out and just eliminate the return itself. Probably be weird stuff. So let's try the little Mycroft program with the GCC inclined compilers and see what we get. So there's Mycroft's little program we produced over here. And if we just straight compile it with GCC, we get this. And this ought to look pretty familiar to you. We've seen this before. We know RDI is the first argument. It holds the head. We know that RSI is going to be the second argument. Let's see if we can find an RSI down through here. I can't find it. My eyes are glazing over. Anyway, so there you go. So we're going to put stuff into the red zone on the stack, and we're just going to store everything in the red zone on the stack and do whatever we do. What am I saying? This is not two arguments. I really need more coffee this morning. I really need a lot of coffee. The function has one argument, x, and it's in RDI. There we go. So RDI gets put into storage on the red zone. I'm saying red zone like you all know what it is. I've covered it before. Basically, this is what's called a leaf function. I've mentioned that before too. It doesn't call any other functions. So nobody is going to mess up its stack. And so instead of reserving space on the stack like you normally would by subtracting from RSP, we just write straight onto the bytes that are on the stack. We just do that. And as long as we don't push anything onto the stack and override it, we're fine. And as long as nothing else pushes something on the stack and overwrites it, we're fine. The one thing, since we don't call anything here, the only thing that might interfere with the stack is an interrupt handler. But the red zone has a guarantee that interrupt handlers won't modify the red zone of the stack. So we're fine. So that's why this is all being written onto RBP minus something. Remember how the stack works, right? It grows downwards. So we're writing past we're writing into the unallocated stack. And as long as we don't call anything, then we should be fine. All right. So all the temporary values are in there, and that's common when you don't have any optimization because it's easier to debug. And so things get moved from memory into registers, and then in here in this case, this is almost certainly a relocation. And then once you've done something, they get moved from memory from registers back into memory. So things get copied out, you do some work and you copy them back. Very common. 54 bytes. The resulting code is way overproduced. If we do -02, which is my favorite optimization level, everybody should have a favorite optimization level, you end up with 33 bytes. And the code is moderately well optimized. It's a little easier on the eye, a little easier to look at. These zeros in here, by the way, are still going to be relocations. Don't worry about them. We haven't fully linked this. We've just compiled it. And so you'll see some places where there are relocations. And it's just way simpler. So here we set EX to 0. We check to see if this is 0. And think about that for a minute. We're checking to see if RDI is null. And if it is, we jump down here and return. And if it's not, we flow through this no-op. And then we go into this loop checking it again. This is the if, while, do while structure that Mycroft gave us. This is exactly the same thing he produced in the paper, just happens to be in IntelliAssembly with the weird no-op stuck in the middle of it for alignment purposes. So there you go. He wasn't just making stuff up when he did that. That's what compilers really like to do. Well, unless you do something drastic. So let's do GCC-OS. This gets it down to 20 bytes. And this OS says basically squeeze the code, optimize for size. And we wind up with something that looks like this. So we still do the same thing. We still zero out EAX. We still test RDI here. But the compiler has done some clever things. So we have to have this test. Back here, we had a test RDI here, and we also had a test RDI here. Well, the compiler has done some additional work to figure out it can reuse this for both cases. So you wind up with just one test at the top, much more like a while loop. It also figured out that we don't need no ops for alignment. They're gone. The no ops are gone. That's handy. And it can reuse this jump to get out of the loop. So before this was using a jump to skip the loop, but now it's unconditionally branching up here and then using this to get out of the loop. So it's done some clever stuff here. Compilers can be pretty smart. And we've gone from 53 bytes down to a mere 20 bytes, which seems like about as good as we could do. Here's Clang. One of the first things you might notice when you go from GCC, which has this nice branch protected target up here, to Clang, which does not, is that target branch protection is not enabled by default in Clang. And so you wind up with this code. And this code really looks like the default optimization level of GCC -02. Looks about the same as that one. If we go back to 02, looks like this. It has a NOP and a NOP and an extra return. This doesn't have the extra return, doesn't have the NOPs. It has one of them right here. But otherwise, it's pretty much the same code. It still wants to align the top of the loop, right? Because it's the top of a loop. And if this loop's going to run a lot, that alignment will help. It does not bother to align this return because it's like a one-shot return, and so it doesn't care. If I say -OZ, the rough equivalent of the -OS for GCC, I can compress it down to a mere 16 bytes. That's smaller than the GCC one, but it looks like it used the same trick, right? I test, I jump out, I unconditionally branch back. It looks exactly the same, but it's smaller. Why is it smaller? It's smaller because it doesn't have the 4-byte NBR64 up here at the top, and that's the only difference. Otherwise, it produced the same code. So these compilers all tend to do the same kinds of things in the end. And so you should be able to recognize structures like this when they pop up in code. So let's pick on the -02 version, because that's a nice one to take a look at, and it's got some stuff going on in it that we can take a look at. And it looks very, very, very similar to the code that Mycroft has in the paper. And let's just walk through it. So the first thing you do is convert it to SSA. And this is maybe a silly thing to do, but we'll try to make it look like the way the SSA was done in the paper. I can't stick a letter on the end because that would be weird. EAXA, EXB, no. I will just stick a number on the end. So one of the things to do is to get rid of details that don't matter. Some extraneous addresses go away. There we go, much simpler. No ops go away. The extra return, right now the returns are right together here. Get rid of the extra return. There we go. Nice, much simpler code. None of that's going to impact the type analysis, right? And a lot of program analysis is figuring out what you can throw away. When you've got if someone gives you a giant program, a giant piece of malware, whatever it may be, one of the first questions you should be asking yourself is, how much of this can I ignore? because otherwise it's just a giant pool of stuff that you don't need to be thinking about. So we've gotten rid of the stuff we don't care about. We can build the flow graph, and it's going to look the same as the flow graph that Mycroft had for the most part. We had an additional little move down here that we don't need because we've used EAX to accumulate our value. We set it to 0 here. We add into it here. And that is, in fact, the return value. So I have to move anything into EAX down here. So it's like, in some ways, it's a little simpler than Mycroft's program, just because. So here's our setup. Here's our if then else. Here's our do while. And we have a few instructions in here too. We still have the join points. So we'll need to create phi functions for those join points. Only thing live here, we would assume, and it is an assumption, is EAX, right? Could the thing we return to read other registers? Sure, it could. It could read RDI. But by the calling convention, we'll assume it does not. So only thing live here is EAX, which means we only need one phi function here. Over here, we'll need two. And so EAX and RDI are live here. We'll need phi functions for those. And EAX is the only thing live here. We'll need a phi function for it. And unlike Mycroft's program, we don't have a third thing in it. EAX and RDI are the only things we ever refer to. So let's add the phi functions. Now, how am I going to add them? I'm going to cheat and I'm going to abuse some syntax. So here we go. I'm going to take the phi of the EAX from above, that's one path in, and the EAX from below, because down here is the other path in, this jump down here. Either I fall through or I branch back. I'm just going to write it out like this so I keep track of what I'm doing. And one of those two is going to end up in EAX each time. Same thing for RDI. Down here at the bottom, I'm going to get the EAX from the top. That would be up here, right, where I take this branch and come down here. Or I'm going to get the EAX from the fall through, which I'll get by just not taking this branch and falling through. There we go. And I stuck them in as moves because it seemed like a fun way to do it. There we go. And now we're going to convert it to SSA. It's very similar to how you'd build a trace table, if you remember trace tables. And we just start adding the suffixes, right? So there's our 0, there's our 1, right? So we start out, we XOR it with itself, storing the result in here. And so this is a little tricky. If we had two different things here, it'd be hard to capture that. Mycroft has this 3-argument process where he has the input, output. And here we have input, output, and input. And that can be a problem for us with the SSA form, but right now it's not. So we'll just keep plugging ahead. Testing RDI with itself doesn't change anything. So we'll just write it like that. Right? Test doesn't change any of the stuff. It just sets flags. And now we know that if you flow through, we wind up with EX1 coming through this way. So we'll just plug it in right here. And we wind up with RDI 0 coming through. So we'll just plug it in here. And we proceed same way. So this would be 2, this would be 1. 2 then becomes 3 down here when we modify it. 1 becomes 2 here when we modify it. The test doesn't change anything. And so we would flow through and we wind up with EAX3. If we fall through here. EAX1 if we take this jump. We'll call that EX4. And if we if we come back from here to here, we get EX3. That's the that's the highest one, and we get RDI2. There we go. There is our completed static single assignment version of the program, and the return value is going to be in EAX4. Okay, the argument of the program was in RDI 0. And so the function signature is going to look like this. Whatever the type of RDI 0 was, and then the results, whatever the type of EX4 is. And I'm putting types around here as opposed to replacing the first character with a T like Mycroft does. This just seems more obvious to me. So let's start applying Mycroft's type constraints. So for this first one, we wind up with this. EX1, type of EX1 is the type of EX0, which is an int. Well, we know that it's not a pointer. Why we know it's not a pointer? Because it's not 64 bits. It's only 32 bits. It's not really a pointer. So is int the right type to use here? It's a 32-bit thing. Let's use this since we can. So we'll say it's a int 32 underscore t, or what if it's a uint 32 underscore t? Maybe it's signed, maybe it's unsigned. I don't know. How would I figure that out? Well, maybe I can see how it's used, and maybe that will tell me. But right now, I don't know if it's signed or unsigned. Mycroft didn't have that problem because he only had signed ints in his little program. All right. So these types, by the way, I'm sure you already know this, come from standard int.h, and these are the ones you should be using. So to make your program slightly more platform independent and slightly more obvious. All right. Then we do a test. This is checking to see if RDI is 0. It's the same as comparing it to 0, basically. And because of that, we wind up with this constraint, right? It could be a 64-bit integer, because RDI is 64 bits, or it could be an unsigned 64-bit integer, or it could be a pointer, right? Because it's long enough to actually be a pointer. We don't know what it would point to, so we're going to call that A. So A is like the little alphas in Mycroft's world. We'll just call it A because we don't know what it points to. It points to something, maybe, or it's an integer. I don't know. For the jump, we got nothing. For this move and this move, where the phi functions, we have some different possibilities here, but they have to be compatible, right? So the type that's in EX1 and the type that's in EX3 have to both be the same as the type that would be in EX2. So all those types have to be the same. So I wind up with this nice long type constraint. The same thing for RDI. Okay, this is an invariant, right? This is the start of a loop, and I know something is going to be true always. So it's a nice loop invariant. It just popped out. So the types can, the point here is the types could diverge as we go through the loop body. But when I get back to the top of the loop, the types all have to have converged back together. All right. So now I start making some changes. So here with the add line, if we apply Mycroft's rule, we wind up with something like this, right? The type of RDI, right there, is a pointer to something of type EX3 at offset 0. And down here, the type of RDI, there it is right there, I got 1, is a pointer to something of type RDI2, right? Because that's what we're moving at offset 8. Okay. So there we go. We get some type information. But all we really know from these two things, right, we don't know that it looks like from transitivity, this must be equal to this, but that's not how Mycroft means it. You just have to embrace his partial function notation. What he means is that the type of RDI is, it's a pointer to this, and it's also got a pointer to this, but they're different because of the different offsets. This just gives you a partial information about it. Could there be other things that are in the thing pointed to by RDI? Absolutely, there could be. We don't know, right? There could be something in offset 16 and offset 104. We don't know. We don't know. This is all we know. We have this little partial information about it, and that's it. And it's okay because this partial information is not inconsistent, right? I didn't get two different things that were at position 0 or position 8, right? If I had the type at 0 and the different type at 0, I would then conclude those two types must be the same. But I don't have that, so I'm okay. All right, so we keep going. Another one of these tests, which just reveals the same information as before, except now we have to use a different thing. We're not sure, is it still pointing to an A? I don't know, that was RDI 0. This is RDI 2. Maybe it's pointing to something different, so let's call that B, and it could be. Okay, so we then proceed on down here. Here's another move. We don't know which one we choose, but we know they all have to have compatible types, and so we wind up with this type constraint right here. And there you go. There's a type annotation based on Mycroft's paper. We still need to annotate the function. We still can't tell if EAX should be signed or unsigned. If you can see it in here, you're doing better than I am, because I don't see anything that clearly indicates one or the other. But you know what? We're just going to pick one, and we're going to pick signed. So there we go. We reduced this down to int 32t, and there you have it. So we just call it signed. In addition, it's pretty obvious that RDI2 is a pointer. So we're going to replace it with a pointer to A. How do we get there? Well, we know that RDI2, right, down here could be one of these things. We know RDI1 is definitely a pointer, right? And we know something about how they're all linked together because of this line right here, right? We know that RDI1 and RDI2 have to have the same type. Since RDI1 is a pointer, RDI2 must also be a pointer. So we can go ahead and solve that. And in fact, it's pointed to A, pointed to A. Now they're all just pointers to A because we can figure that part out. Because we can conclude that A and B have to be the same. But we have this. We have pointer to A, but we also have these guys and this pointer. How are we going to solve that? So we know T of RDI3 is a type of RDI2, which is this pointer, which has, look at that, RDI3 in it. So we're going to fail a curse check. And Mycroft tells us that when that happens, we come down here and invent a struct to make our problem go away, to hide our problem. And here's the struct we would invent. And we didn't just make this up, right? We know the type for EAX3, right? We know it is an int32t, so that's what we put here. And for some reason there's a U there. It shouldn't be a U there. I'm just tired when I made these slides. And then for RDI2, we also know it's a pointer. And in fact, we can figure out that it's a pointer to a struct. So because we know that this has to be the same as this, these are all the same, so it must be a pointer to the same structure we're just now inventing, and there you go. So with that in, we now have a uint32 at offset 0, a pointer to a struct x at offset 8. RDI2 is just a pointer to that structure. We can also fill it in up here and even up here. And so we can make all this more C-like. Let's figure out the function signature. At the very end, we are returning EAX4. In the entry, we have RDI 0. So we know that the type of RDI 0 is a pointer to a struct x. So that's our argument. And we know that at the end, EX4 is the type of EX1. The type of EX1 is an int32t. So we know that the return value is of type int32t. And there's our function signature right there. And that's it. Wow, got that way faster than I thought I would. This was a lot. And it's super intuitive for some people, and it's not super intuitive for others. And this is basically what you get from Mycroft. It gives you a way to generate a plausible set of structures in your program. And if you want to see how well it does on programs, write some code, compile it, and then run it through Ghidra. And you'll get to see, because Ghidra does this. Ghidra tries to figure out using this approach how types are used. If you dig around in the settings, you'll see it's one of the things that it does when it performs the initial analysis of your program to try to decompile it. And if you are struggling with trying to figure out what a program does, knowing something about like this, just this level of information about this blob of code is huge, right? This tells you I've got one argument and one return based on what I know. And if you combine this with live variable analysis, it's an even stronger statement, because now you know that there truly will be just one argument. So there's another basic technique. This is a basic technique for program analysis, very widely used, very widely deployed in compilers and decompilers and just all over the place. Whew, that's it for today. I'm gonna give you some time back today because I have to go to the lab. But that's fine. Next time, we're going to begin to talk about satisfiability and SMT, because we're running out of time to talk about them and it takes a while to go through them. And this is going to be where we'll get some of the answer to questions like, how do I detect that there's an opaque predicate?